Hello everyone, welcome to this series of lectures on the course Calculus and Numerical Methods. With this video, I'm starting with the second half of this course, that is numerical methods. So under this second half, that is numerical methods, today we are going to look at the first chapter titled Solutions of Transcendental and Algebraic Equations. Under this, we have the first method called as bisection method. So before starting with this bisection method, let us recollect some terms which we have already learnt in our lower classes. So I believe everyone knows what's a function, right? So I assume that you all are knowing what is a function. Now, what is the root of a function? Supposing f is a real valued function defined on a closed interval ab. A real number c in that closed interval ab is called a root of that function f if f of c is equal to 0. That is, the value of the function f at the point c is 0. If this is happening, then the real number c is called the root of this function. Now, geometrically speaking, how will it look? Supposing I have my x-axis and y-axis. And supposing a is here and b is here, right? So, and supposing my function is starting from here, and supposing it is going this way, and it is, let's say it is coming till here, and this is the end value b of the interval, which is the domain of this function, right? So f here is a function from closed interval ab to r, which I've plotted here. Now if you see, the roots of the function are the points where the graph of the function touches the x-axis. So this is my x-axis here and this is my y-axis. So the point here that you can see is nothing but the root of this function. This point, right? So I think it's become too dark. Yeah, now I can do it this way. Yeah. So this is the point C that I'm talking about in the definition. If there is such a point C, then that point C is called the root of that function, right? Now it is possible that a function has more than one roots also, then the graph will be touching the x-axis more than once. Okay, so this is how geometrically the root of a function looks like. Now let me take an example of a function and let's try to see which are the roots of that function. Consider the function f defined from the closed interval 0 to r, and it is defined by f of x is equal to x square minus 1. Now if I want to find the roots of this equation, then I can set it equal to 0 and then I can solve it. F of x is x square minus 1. This means x square is equal to 1, and this tells me that x is either plus 1 or minus 1. But if you see, minus 1 is not there in the domain of the function, right? Because my function is defined in the interval 0 to 2 and minus 1 is not coming in that interval. So I'm going to ignore minus 1. Minus 1 does not belong to the closed interval 0 to. So we ignore this minus 1 and hence the only root of this function is 1. Now if you try to plot this function in your xy plane, how will it look like? Yes, so this is my y-axis, this is x-axis, and let me mark some points 1, 2, This is my positive x-axis and negative x-axis, and this, supposing this is my y-axis, right? So at x is equal to 0, the value of the function is -1. So I'm here. I'll put that in a different color. Yeah, let's say red. So I'm here at x equal to 0. At x equal to 1, if you see, f of x will be 1 square, that is 1 minus 1, that's 0. So the function will be here. And at x is equal to 2, it will be 2 square, that is 4 minus 1, and that is 3. Supposing I have 3 here. So at x is equal to 2, it will be somewhere here, more or less. This graph is not exact. Okay, so I'm just drawing a rough sketch to give you an idea how the graph will look. So the graph will be somewhat like this. No, just assume that it's coming properly. Yeah. So more or less somewhat like this. And if you see now, the root we have found out to be 1, and at 1 the graph is actually touching the x-axis here. Okay. So the graph will be touching the x-axis wherever the function is having the roots. Geometrically, it means this. Alright. Now this bisection method which I'm talking about, it is based on one important theorem that we study in calculus. Okay, so I will just state that theorem. So the root of that function was 1. Okay. So this theorem says, if I have a function f from closed interval ab to r which is continuous, such that the value of the function at a when you compute, that is f of a, and the value of the function at the point f of b, and you take their product is negative, then this theorem says there will be at least one point in this interval a comma b, namely c, such that the value of f at the point c is going to be 0. Okay, such that the value of f at that point c will be 0. Now when I say f of a into f of b is having negative sign, what does that mean? I have two real numbers. The codomain is the set of real numbers. So f of a and f of b are real numbers, and product of these two real numbers is negative. What does that mean? That means f of a and f of b are real numbers of opposite signs, right? So I need a continuous function on some interval a b such that the value of the function at a and the value of the function at b, they have opposite signs. One of them is positive and the other one is negative. I'm not worried about which one is positive and which one is negative. I only need that one of them is positive and the other one is negative. Then their product will be negative. So if these conditions are satisfied, then this function will definitely have a root in this interval AB. Okay, this is what this theorem says. Now, if I try to understand this geometrically, let me draw the graph. Supposing this is my xy plane, and let's say the point A is here, the point B is here. Now f of a and f of b are of opposite signs, so I will just assume that f of a is positive and f of b is negative. Okay, anything, you can also consider the other case. So I'll assume that f of a is positive, so image of this point A is positive, so it will be somewhere here. right? So this is the point f of a, and this is that point a comma f of a when you plot it on the graph. It lies here. And f of b is negative, that means it has to be below the x-axis somewhere here. So the corresponding point will be here, f of b, and this is that point b comma f of b, right? And f is a function from a comma b to r which is continuous. That means it cannot break in between. So it has to come this way, somehow it will come, and at some point it will have to cross the x-axis and it will have to go to the point B, right? So while traveling from this point to this point, definitely it is going to cut the x-axis at least at one point. The function cannot break. The function cannot come this way and it can break here and it cannot continue from here because the function is given to be continuous, right? So such a case of breaking the function is not possible. So when it is traveling from this point to this point, it will definitely touch the x-axis at least at one point, and this is that point C which I am talking about. And at this point C, the value of the function will be 0, and this point C is going to be the root of that function. Clear? Now second possibility is that why only it is touching at one point? It could touch at many points. So follow the graph which I am drawing in the red pen. So it is possible that the function comes this way, it goes again this way, and then it comes back, then it goes again, and then it comes back, and then it comes to B. This is also possible. This is also a continuous function. Now in this case, how many roots I am getting? This is one root here. This is the second root. This is the third root. This is the fourth root, and this is the fifth root. So the statement says at least one root is there. There could be more roots as well. All right. So this is the result on which the bisection method is based. All right. Now, why this bisection method is useful? The example that I took here was a simple example. This is an example of an algebraic equation, meaning it contains terms of the form x power n only and constant terms. So whenever I have such expressions with up to order 4, maybe there are some standard methods using which you can find the roots. But imagine you're having a function which is having more than degree more than 4. Then it becomes very difficult to solve it. And that is when the bisection method comes useful. Okay. Another thing is the functions like trigonometric functions, sin x, cos x, or logarithmic functions or exponential functions. These functions are called transcendental functions. Okay. These functions are called transcendental functions. So whenever you have functions which are involving these functions, for example, I can say 1 plus root of 2 minus sin x. There is no standard way to solve this equation, to find the roots of this, right? Or I can make it more complicated by adding log x. So bisection method helps us to find roots of such functions if the roots exist. Okay. And only disadvantage of the bisection method is it will give you a approximate root. It might not give you the exact root. Okay, but it will get you very close to the exact root. It depends on how many iterations are doing, that I will be demonstrating in the example to come. Okay, so bisection method which I will be doing now, it will give us the approximate root of that function in the given domain. Okay, so let's see how this bisection method works step by step. B to R, which is continuous, And let's assume that f of a and f of b are of opposite signs. So assume that f of a into f of b, their product is negative. Okay, so without loss of generality, I'll assume f of a is positive and f of b is negative, right? So let me draw the graph just for a better visualization. So supposing this is my x-axis and supposing I have my y-axis here. Let's say this is point A and this is B, and let's say the function is somewhere like this. So from A it is defined till the point B, so I'll draw it. Yeah. So f of A is positive and f of B is negative. That's here, right? And it's a continuous function also. This is x-axis and this is y-axis. Now what we do here first is we take the midpoint of this interval AB. The point A is here and B is here. So we bisect the interval AB. Okay, and I will call that point as x naught. So let x naught be the midpoint of A and B, that is given by A plus B by 2. So that midpoint x naught which I am talking about will be somewhere here, right? So the x naught point which I am talking about will be somewhere here, which is the midpoint. Then what you do is you find the value of the function at the point x naught. Okay, find the value of the function at the point x naught. So compute the value of the function at x naught. If this value is 0, it's a real number. So by law of trichotomy, it is either 0, positive or negative. If it is 0, then this point x naught is the root of this function. Okay. If it is positive, if this x naught is positive, then when you take its product with f of a, which is already positive, so f of a into f of x naught, both will be positive and their product will be positive. And then we are going to discard the interval a comma x naught. And because if f of x naught is positive, that is the first case, and f of b is negative, that's the assumption. So product of f of x naught and f of b would be negative. So we are going to retain this interval x naught a, and this a from here, which is here at present, I will call this x naught as a. I will rename it, and this will be my interval if f of x naught is positive. If f of x naught is negative, which is happening in this case, f of x naught is here, which is negative, then I have to look at f of a and f of b now. F of x naught is negative, so take its product with f of a. So this is positive and f of x naught is negative, right? So their product will be negative. So these two will be of opposite signs. That means I'm going to retain this interval a x naught and I'm going to discard the remaining half, that is x naught to b. Clear? So what I do now is, now I will pick up this interval. So this b which was here, now I will rename this x naught as b. So this b from here I will bring it and I will keep it here. So I have again the interval a comma b which is renamed. Okay. So what I do now, a I keep as it is and you choose b is equal to x naught. Clear? So I have this interval. Now what I have done, we knew that between a and b there is at least one root. which was a bigger interval. So we have divided that interval into half. And in this interval now, definitely there will be a root. Okay. So A we will keep as the same point, and B is the new point B x0 which we had found, which is the midpoint of A and B. That is our B. Okay. Again, of this A and this new B, I will find the midpoint. Supposing that midpoint is, let's assume that it is here. Okay. So you compute x1, which will be the midpoint of A and B now again, and you call it x1. So this is the point x1 which I am talking about. So midpoint is found. I named it x1. Now you compute the value of the function at this point. Okay, you find f of x1. If f of x1 is 0, then x1 is the root of this function and we are done. We have found one root. If no, then this f of x1 has two choices, either positive or negative, right? Now if f of x1 is positive, in our case f of x1 is here, so it's a positive number, right? F of x1 is positive, looking at the graph. So when I take the product with f of a, this is also positive, so their product will be positive, which is the product is positive, but I want the product to be negative so that the root is there inside that interval, right? So now I'm going to discard this point a from here, a to x1, this interval, half of the interval we are going to discard, and f of x1 is positive and f of b is negative, right? So their product is going to be negative because one is positive, the other is negative, correct? So this will be a new interval now, and this x1 we are going to rename x1 as a. So a will come here and a will disappear from here. So again we have bisected the new interval that we had obtained, and right now we have the interval a to b here, and in this smaller interval now there will definitely be a root because f of x1 into f of b, their product is negative. So by the theorem that I saw in the previous slide, it will definitely have a root, as you can see in the graph also, right? So the new interval AB is there, so I will choose now A is equal to x1. Rename x1 as A. Again I have the interval AB with me, and again I will do the same process. So I will find the midpoint of A and B now, that is here, and I will call it x2. So you let x2 to be the midpoint of new A and B which I have obtained. Okay, now A is here and B is here. So this is x2. After taking the midpoint, you compute the value of f at the point x2. So you compute f of x2, right? If f of x2 is 0, then this x2 is the root of the function and we are done with the problem. Okay, so if at any stage you get f of x2, f of any point to be 0, then that particular point is the 0 and we are done. We have found the root. If not, this could be either positive or negative. In our case, image of x2 is here. So it is negative, right? So f of x2 is negative, and I know that f of a is positive, f of x1, correct? So their product will be negative now. Whereas in the other half, if you see, I won't get anything because their product will be negative into negative. F of x2 and f of b both are negative. So their product will be positive. So this x2b will be discarded now. And what I'm left with is this a comma x2. x2 is this point now. So I will remove this b from here, and x2 I will name it as b, right? So whatever I'm marking in red now has been discarded from the original interval AB. At this stage, we are here. Whatever I'm marking right now has been discarded, and we right now have the new interval AB, which is far smaller than the original interval AB. Correct? So in this way, you keep on dividing this interval, and if you see, you are coming closer and closer to the root. Okay, the root is sitting here. This is the root. And at each step, you are coming closer and closer to the root. Okay, so depending on what error you can tolerate, depending on that, you are going to stop the process and you are going to get the approximate root. Okay, so when I say error, it means I won't be getting the exact root in a finite number of steps here, right? So our aim is to get the approximate root up to a certain level of error. Okay, so in the question, it will be mentioned up to what error you can find the root, and accordingly you have to find the root, that approximate root, keeping in mind the error that is given to you. Secondly, someone can ask you to compute maybe the first 5 iterations. So this is the first iteration that we did with x0, then with x1 is the second one, with x2 is the third one. This way someone may tell you to compute first 10 iterations in a problem, and at the 10th iteration, what is the root, approximate root? That could be another question. Okay, so depending on the question, we will see both kinds of examples we are going to do. Okay, so this is how the bisection method works. At each stage, you bisect the interval. That's how it gets its name as bisection method. And slowly, as you increase your iterations, you are coming closer and closer and closer to the root. Now again, this new a, b, if you take, again if you divide, you find the midpoint. This will be x3. And still I'm coming closer to the root c. This will be the new interval that I'm getting. Then you'll close this b and your b will come here, and the new b is still smaller. Understanding? So this is how the bisection method works. So I'll end the video here. So I have explained the idea behind the bisection method, and in the next video I will be solving 1 or 2 examples demonstrating how you actually find the approximate root in bisection method. All right.